So since we've been looking at solving exponential and logarithmic equations, today we're going to be looking at some examples. So we'll bring back some of the formulas that we looked at over the last couple of weeks. We'll start with number one. Suppose you deposit $2,400 in an account that pays interest compounded continuously. So this is our keyword for which formula we're going to be using. Your goal is to have at least $3,000 in your account after 5 years. What is the interest rate that is required to achieve this goal? So that continuously should be tipping you off that you're going to be using the equation A is equal to P times E to the RT. So there's going to be some things that we need to pick out here. So I'm going to figure out what we have for A, if we have anything for P, if we have anything for R, and what we have for T. So we're starting with $2,400. So that's our initial or our principal or our P. So 2,400 is our P. Our goal is to have at least $3,000 in the account after 5 years. So that's our ending amount. So that's going to represent our A. And then I want to know what the interest rate is that's required. So my R is what I'm looking for. I don't know that. And the time period is 5 years. So T is 5. So if I set up my A is equal to P times E to the RT, and I plug in what I have, 3,000 is equal to 2,400 times E to the R times 5. So I know that I need to get this base of E by itself. So I'm going to go ahead and divide each side by 2,400 to get rid of that. So 3,000 divided by 2,400 is 1.25. That's going to leave me with E to the 5R. I'm just switching those around. I can multiply in any order, so I'm just writing it as 5R. And then I need to undo the base of E. So that means that I'm going to take the natural log of both sides, because that is what is going to undo my base of E. So ln of 1.25 is equal to ln of E to the 5R. And I'm going to stick with this ln of 1.25 on the left-hand side. We know that the inverse property tells us that ln and E undo each other, so I'm left with 5R on this side. And then I'm going to go ahead and divide each side by 5 to get the R by itself. So that's going to give us a decimal. It's going to give us R is approximately 0.0446. But remember that interest rates are generally written as percentages. So what I'm going to do is I'm actually going to go ahead and move that decimal point over to the right 4 places. So that's going to tell us that our interest rate is about 4.46%. So that's the interest rate that we would need to get our bank account to have $3,000 in it after 5 years. Let's look at number 2. The number of Baconburg birds in a forest is decreasing by 3% every year. So here's our keyword here, decreasing. Originally, there were 5,400 Baconburg birds. When will the population of birds be halved? So if we're talking about decreasing, we're talking about exponential decay. So that tells us that the formula that we want to use is A is equal to P times 1 minus R to the T. And since we're decreasing, that's why we're using the minus in there. So I need to figure out what I have and what I need. So I'm going to write out my variables again, A, P, R, and T. So I know that my percentage is 3%, so that's giving me a rate. So my rate is 3%, but I know that in my problem, I need to go ahead and write that as a decimal, so that would be written as 0.03. We're saying originally there were 5,400 Baconburg birds. That means that we're starting with that, so that's our P. So P is 5,400, and I want to know when the population of birds would be halved. So basically, if I'm starting with 5,400 birds, and I'm having that means I'm dividing by 2. So that means that the ending amount here is actually going to be 2,700. So that's the amount of birds that are going to be left at the end. So what I'm looking for is time, which makes sense because I'm asking when. So that's representing a T value. So if I go ahead and plug in what I have into this decay formula, that's going to give me 2,700 equal to 5,400 times 1 minus 0.03 raised to the T. Again, I'm writing that rate as a decimal in there. So first thing I'm going to do is follow order of operations. I'm going to go ahead and simplify inside here. So 2,700 is equal to 5,400 times 0.97 raised to the T. And my base here is the 0.97. So I have to get this expression by itself. So I'm going to undo the 5,400 by division on both sides. So when I divide 2,700 by 5,400, that's actually going to give me 0.5, and that's going to leave me with 0.97 raised to the t. So this is the base that I'm trying to undo here, and I'm going to use my inverse property, and I'm going to take the log base 0.97 of both sides. So log base 0.97 of 0.5 on the left-hand side, and that's going to be equal to log base 0.97 of 0.97 raised to the t on the right-hand side. And we know that this operation is an inverse. It undoes itself. So all we're going to be left with is the t on the right-hand side. So I'll carry my work up here. So that's going to give me log base 0.97 of 0.5 is equal to t. And this is where I need to use the change of base formula. So that's going to tell me that this is log of 0.5 divided by log of 0.97, and that's equal to t. And when I go ahead and do this division in my calculator, I get a t value of approximately 22.8. And this is going to be in years. So it's going to take me about 22.8 years to half the population of the birds that we started with. The third example is going to be talking about growth. So a population of Baconburg starts off at 20,000 and grows by 13% each year. And grows is our keyword here. We want to determine how many years before the population of Baconburg has doubled. So if we're talking about exponential growth, we're using the model A is equal to P times 1 plus R to the T. And we're using a plus because we're growing. So I'm going to go ahead and label out what I have here. So A, P, R, and T. So we're starting at 20,000. 20,000 is our starting or our initial value. So I'm going to put that as P. We're growing by 13%. That's a rate. Again, I'm going to write that as a decimal. So 13% is equivalent to 0.13. We want to determine how many years. So we're looking for time. We don't know what the time is before the population of Baconburg has doubled. So if I'm starting with 20,000 people and I'm doubling it, that means I'm multiplying it by 2. So that means that my ending amount is 40,000. So that's my A. So when I go ahead and use these values and plug into my growth formula, that's going to give me 40,000 is equal to 20,000 times 1 plus 0.13 raised to the t. I'm going to use my order of operations here, simplify inside the parentheses. So 40,000 is equal to 20,000 times 1.13 raised to the t. And my base here is this 1.13. So I need to get this expression by itself. So I've got to get rid of that 20,000. So I'm going to go ahead and do that by division on both sides. So divide by 20,000, divide by 20,000. That's going to give us 40,000 divided by 20,000 is 2, equal to 1.13 raised to the t. And here again is my base. So my base here is 1.13. I need to undo that by taking log base 1.13 of both sides. So take log base 1.13 of 2 on the left-hand side, and I'm also going to do the same thing on the right-hand side. So log base 1.13 of 1.13 raised to the t on the right-hand side. So again, this is an inverse operation. This undoes itself. We're left with t over here. I'm going to rewrite over here. So that's leaving me with log base 1.13 of 2 equal to t. I've got to use change of base again over here. So that's going to give me log of 2 divided by log of 1.13 is equal to t. And when I divide that using my calculator, that's telling me that t is approximately 5.7 years. So it's going to be your turn to try some practice problems. Let me know if you have any questions.